Hello and welcome to the Drexel interview. I'm your host, Paula Marantz Cohen, speaking to you from my office as Dean of the Pennoni Honors College at Drexel University in Philadelphia. Today my guest is the eminent psychologist and neuroscientist, Michael I. Posner. Dr. Posner is an emeritus professor of psychology at the University of Oregon's Institute of Cognitive and Decision Sciences and an adjunct professor at the Sackler Institute of the Weill Medical College in New York. He has a long-standing interest in the way the brain works and its capacity for change. Michael Posner, welcome to the Drexel interview.
Thank you very much. Happy to be here.
So you majored in physics in college and went on afterward for a brief while, I believe, to practice or to work in physics before turning to psychology. And I think that's interesting, physics being a hard science, psychology being perhaps softer. Could you tell us a little bit about that shift?
Well, physics was a very romantic field for me. I loved it a lot, but it was, as you say, too hard. I always wanted to teach. I knew that I would never be able to teach physics. I didn't have strong enough grasp of the field. So my brother said, why not try a biological science? And I ended up with psychology.
And cognitive psychology in particular, which in a way seems to me to be that bridge between maybe your physics interest and psychology as it might have traditionally been thought of.
That's true, but when I started, there was no cognitive psychology. There was only psychology. I did things that people called information processing psychology because of their relationship to information theory. And only later, after Ulrich Neisser wrote a book called Cognitive Psychology, that name got associated, and I used the name too.
So you were a trailblazer in the sense of creating that field, or at least helping to name that field.
But Neisser was the crucial person.
Can you define cognitive psychology?
Well, it's the study of mental processes, and generally cognitive psychology was defined by software. That is the programs of the brain. And the idea was that that was a distinction between psychology, cognitive psychology, which dealt with the software, the programs, and the hardware of the brain, which was left to physiologists. At that time.
At that time. And now when we think of cognitive psychology, what do we think of?
Well, there's a distinction. Of course, the current name for what I do is called cognitive neuroscience. It's because the human brain has become accessible to experimental analysis now through the development of neuroimaging. It's possible to look at the brain, maybe not in its ultimate detail, but to look at the brain while one does something like talk or go through an interview. So you would probably expose the emotional responses to your questions, as well as the areas that are involved in understanding what you mean and orchestrating my speech.
Oh, I wish we had done that, where you were attached to one of those fMRI and we could find out what actually is going on as I'm interviewing you.
I was attached to neuroimaging equipment in the start, and we did work on the ability of people to process, first me and then others, to process language and to produce language.
Well, I want to get to that. I want to get to the fMRI work you've done. But actually, you began in the 1980s with more primitive technology, with PET scans, right? And that was the first, you looked at brain-damaged individuals and looked at what was going on with their brains when they responded. Could you talk about the early work?
Well, I did work with brain-damaged people in Portland, Oregon. This was prior to my involvement with neuroimaging. I was interested in the localization of the kinds of mental operations that were studied by cognitive psychologists. So a task like listening or even shifting attention from one location to another, these are tasks that can be broken down into underlying mental operations. And I was interested in seeing if we could make connections to the cellular structures that were being studied in attention in monkeys. And so I worked with patients that had lesions of various places in the brain to see if there was interference with particular mental operations. They all would be said to have attentional problems, but it turned out that depending upon the exact location of the lesion, the problems were quite different. And so I satisfied myself that mental operations were localized in different brain areas. But I knew that working with lesion patients would never satisfy everyone in the field because, of course, their brains are upset by the lesion and therefore differently functioning than normal. So I always looked for a technology that might allow me to test my hypothesis. And that technology came around in positron emission tomography, the first of the neuroimaging techniques that allowed study of the living brain while it performed tasks. So I went to St. Louis, Missouri, where they had positron emission tomography under the control of a very brilliant neurologist, Mark Rakel. And Rakel and I worked together to see if we could understand the localization of mental operations. We actually used language.
Now, these were in normal brains?
In normal brains.
So you moved from looking at these lesions in brain damaged people to wanting to know how the brain works as a normal, in its normal state.
Right. I wanted to see if the theory that I developed in one area would actually illuminate some of the issues in the normal brain.
And your focus, was it from the beginning on this issue of attention?
Yes, my focus was on attention, but that's not what we imaged when I went to St. Louis. We dealt with language. There's an ethical issue in using these early neuroimaging methods like positron emission tomography. It involved the use of a small amount of radioactivity. And that's a serious issue. That's an important issue. Maybe not so much for the person who's running, because the FDA didn't allow anything to be done more often than every 6 months, but particularly for people who are running the experiment. So we wanted
Namely you.
Yes, me and others.
Yeah.
We wanted to work on a topic which had critical importance to management of the brain during neurosurgery. Something that would illuminate and help neurosurgeons to use a less invasive method than they were already using, which was water testing involving threading a catheter up through the carotid artery and anesthetizing one hemisphere or the other to see exactly where the language areas were. Positron emission tomography, we were able to look at the underlying mental operations and understanding a word. Those are, if you're reading the word, visual operations, phonological operations, semantic operations, and attentional operations. And we were able to localize these operations in different areas of mostly of the left hemisphere. And we felt that would be useful to neurosurgeons and also advance testing of the hypothesis that I had about the localization of mental operations in different parts of the brain.
So has this actually had an effect on how neurosurgeons operate? And the second part is, were you very exposed to this radioactivity?
I wasn't very exposed. None of us were. And far as I know, no one who worked in those experiments has suffered any damage. It's just that you have to be extra careful with these issues because, of course, you want to discover something, but you don't want to hurt anyone. We did carry out the experiments. They had a large effect on the field. They had a delayed effect on the actual use of this information to replace water testing. But later, fMRI certainly has been used in many of the neurosurgical situations to replace water testing, and it is much less invasive, in fact. Pretty much entirely benign as far as its effect.
The use of the fMRI,
yes.
And that was within the last, would you say, 15 years?
Yes, it really developed from a discovery at Bell Labs by Ogawa, and he found a way to use a high-level magnetic field to look at brain activity, a relationship to brain activity, so-called bold response, which was based on the idea that hemoglobin, the red blood cell content, is paramagnetic. It builds up in areas of the brain when they're active, and that can be sensed remotely in a high magnetic field, and that's the basis of functional magnetic resonance imaging.
Okay. You use this technology for the very young and the elderly, and I want to, in the course of your career, I want to talk a little bit first about infants and the work that you did with attention with infants.
We used high-density electrical recording. You can localize the areas of the brain that are active. Then you know where the signal comes from. Once you know where the signal comes from, you can predict the distribution of electrical activity across the scalp. You can't go in the other direction. It's too hard. But you can go in the direction between knowing where something is from MRI to predicting what the electrical pattern will be.
Okay, so in the case of these infants that you were studying, the idea was attention and focus, and you noticed that infants of 2 to 3 months had great difficulty disengaging their attention from an object, and at 4 months they began to be able to shift their attention from one object to the other. And you related this is fascinating to me, with the ability for self-control. Is that right? Am I summarizing this correctly? I'm probably getting the layman's very generalized
in
idea.
Part, yes. One early control network turns out to be what I call the orienting network of the brain, which is a kind of combination of frontal activity and parietal activity. And in early life, it's the major control system. Of course, the parents are also a major control system, but self-control is exercised through the orienting system. It's quickly surpassed in importance by another brain system, which I've called the executive attention system, and sometimes it's called the cingulo-opercular system in anatomical terms, MRI terms. And we also trace the development of that beginning as early as 7 months, when we found that error detection, the infant could detect an error and used exactly the same areas of the brain that were used by adults. So we knew that at least by 7 months, error detection was online, though it didn't control the infant's behavior the way it does the adult behavior. So it didn't have good connectivity to other areas of the brain.
So how did you know that it was this executive function was operating, just because that certain section of the brain?
Because error detection is a very important aspect of executive function. When you detect something that's not correct or right, either self or from the display, and that has a particular signature in adults. We found the same one, same electrodes.
But it was
the
the act, the behavior was not there to be manifested in
because
infants.
if you made an error in our typical experiment, you would slow down on the next trial to kind of avoid an error. That skill doesn't develop till about 3 years.
I see.
So,
now, I'm interested, though, getting back to this idea of self-control. And its connection to, obviously, to maturing properly and becoming an appropriate adult. And I would imagine that's also connected to error detection and the ability, what you just said, to slow down. Are these all connected? And when something goes awry in one of these areas, you get children who have problems with, say, attention deficit or other sorts of behavioral problems?
Well, there are definitely great individual differences in the development of the executive attention system, which is a self-control mechanism. We know a lot about the areas of the brain that are involved, and we do know something about these individual differences and when they're deficit. Not all things that are called attention deficit disorder, however, are likely deficits in this system. There may be other systems, other attention systems, for example, the frontal parietal system, that may also be deficit.
So it's not one spot in the brain.
It's not one. What we learned from our original language studies and from just about all the MRI studies that have gone on is that there's always a network of areas that are tied together. So what's localized isn't a task, so you can't say language is localized in some area or attention is localized. What it is a mental operation that's localized, a part of that task. Cognitive psychologists have taken tasks and divided them into these mental operations, and that turned out not to be exactly true every place, but a good clue as to how the brain actually organizes these. And by recording with high-density electrical things from the scalp, it's possible to get the time dimension, how quickly one area of the brain gives rise to the activity of another area.
So it's a complex system,
So
obviously.
it's a complex network, and we have come some way, certainly not all the way, to understanding how it works in real time and what some of the deficits might be.
Has this ability to see this complex system helped with treatment of various disorders?
I don't think it's helped with very many current treatments, but in fact I'm here in Philadelphia to describe our efforts to try to understand how we might use what we know about networks of the brain that are involved in executive control to actually improve executive control, certainly in people that have deficits, but also possibly in others.
But I guess the identification in and of itself is useful to parents, to teachers, to others. I mean, you made an interesting statement before when you said that, you know, the issue of control, partially from the, you know, from the brain and partially from the external environment, right? The parents and the teachers and all that. And where those two come together, it seems to me, is a complex question.
Well, it's a very complex question, but it's definite that they do come together. That is,
they
that you can
reinforce
change
each other.
the brain either through one method, experimental method, but of course in real world that's being changed all the time by the experience the child and also the adult has.
Yeah. I was also reading about your work, some of the disorders that you made a connection to, if I'm not mistaken, are connected to self-control and conflict resolution, at least as you were able to discern it through some of this study of the brain. Is that true?
Some of those disorders, yes, they have different networks in which they're implemented, but they all would benefit from increased executive control of the through the attention network.
But I mean, maybe somebody with dyslexia, there could be so many environmental as well as brain functioning factors involved.
To me, it's greatly illuminated all reading, either by dyslexics or by normals. You know, there was a tremendous conflict between two different groups that believed that you needed to teach phonology, and groups that thought if you taught people to read things that they were interested in and they did a lot of reading,
it would happen automatically.
Then they would learn. And we've learned that there are two really quite distinct areas of the brain, one of them related to phonology, and the other related to chunking the letters of a visually presented word into a unit. And really, the phonology allows the person to operate as a reader, to sound out things that maybe they've never even seen before, or to give legitimate sounds to even things that weren't English words. So that's very important for establishing the reading. But a person who has a good phonology but no development of the visual word form system isn't a fluent reader. They can read, but they aren't a fluent reader. They don't do it with enjoyment. That depends upon a later development of this visual area which chunks the letters into words.
So it's not an either-or situation.
It's not an either-or, and it has very particular areas of the brain. Of course, there's much we need to learn, but I think that when I talk to teachers about this, they feel they've learned something about what the nature of the problems that their children are having, whether they be called normal or dyslexic. All children have some problems acquiring alphabetic language. It's not a built-in evolutionary selected skill.
That's so interesting. But it also sounds like from what you're saying that the sounding out, say, of words, which is how I was taught, I guess, to read, but then the later chunking would come later?
Yes, it comes later, generally goes over a long extended period, and it really depends on actually exercising the reading skill.
Very, very interesting. I want to shift to your work with elderly people and meditation and this strikes me as such a fascinating area, especially right now with an aging population and with the great popularity of meditation, mindfulness as a trend in our culture. Can you tell us what kind of work you've come up with in that area?
Yeah, I'm not an expert in meditation itself. I had worked with an expert, a man by the name of Yuan Dong. He approached me and wanted to develop experiments that might convince Westerners, he's Chinese in background, now living in the United States, that this meditation effect were genuine. And he had the ability to develop this skill rather quickly. And he had found changes in both behavior and brain activity in China rather quickly. And so we were able to use a lot of controls like random assignment, an active control system, and so on. It's hard to assign people to all the practice necessary to be a Buddhist monk because that would be thousands and thousands of hours.
Yeah.
But we first started off with 5 days and later did 1 month, half hour a day for 20
Did you meditate
days.
as well?
I was in some of the groups, but I'm not a really practiced meditator. But we've observed many brain and behavioral changes, improvements in attention, reduction of the stress cortisol, the cortisol, that's cortisol, which is related to stress, and mood changes and so on. But among those changes, which was more controversial, was changes in the white matter, that is the connectivity that connects this central area of the brain self-control system to other parts of the brain. So we found this with magnetic resonance imaging. We used a version called diffusion tensor imaging and traced these changes in white matter within a month after doing meditation, always in comparison to an active control. So we published this in 2010 and 2012, but I think it wasn't really believed by most people.
It's so interesting and exciting.
Yes, it's
true.
exciting, but there's
I want to run off and meditate right now.
There's reason to be skeptical.
Are you skeptical of it?
I was then.
Yeah.
But I kind of convinced myself it was true, but it was an MRI statistic linked to changes in white matter. It wasn't actually observed white matter. It was a statistic that tells you how directional the water molecules diffuse in particular things, and they're supposed to diffuse along axons, and as the axons improve in connectivity, that you get higher, it's called FA, but you get higher scores. But it's indirect, and also it was a little hard to see how is it that holding your attention in the present in a non-judgmental way, how does that lead to changes in the brain's white matter, to a physical change? So I did quite a bit of reading and came up with a hypothesis that it depended upon a particular rhythm of electrical activity that occurs with meditation. It's called Theta Rhythm, over the frontal midline where the executive attention system is. It's a crucial node of the attention system.
Well, it sounds a little complicated, but the rhythm, in other words, that habit of a certain kind of thought affects
the brain's
patterns
rhythm.
in the brain's rhythm.
So we used an animal model, mice, to impose rhythms and to see if the white matter changed by viewing the white matter directly using electron microscopy, 16,000 times magnification. So you could actually see the white matter rings around the axon. And we've shown that, in fact, that rhythm does, and related rhythms, do change the connectivity through this white matter
That is
change.
so fascinating.
And now we're trying to take that insight and see if we can take that back to humans. You say, well, why don't you just teach them meditation? Well, meditation does change white matter, but only in the areas that meditation affects. And it's not all areas of the brain, it's just some.
Right,
But
but it's
people
still
have-
some white matter.
Yes,
Yeah.
it is, as far as we can tell. But we would like to be able to change white matter wherever there was a deficit.
Ah.
And so we're working on that issue. That's what I'm going to describe
Well,
what our progress
we're almost
is.
out of time, but I'm struck I'm a great follower of the philosopher and psychologist William James, who is a great proponent of the idea of habit and practice toward changing the self in some way. I mean, he's writing in the 19th century, and it strikes me that this is the postmodern extrapolation of some of what William James was
Of course,
talking
all
about.
psychologists have read William James, so I may have got most of the ideas from the same place.
Oh, great. Okay. Well, thank you so much, Michael Posner, for talking to us today. And thank you for joining us at the Drexel interview.